Hello and welcome to this stream ecology lecture on human pressures other than climate change. So we're going to deal with a number of very major human impacts on stream systems and how it affects their ecology. And I want you to be thinking here about everything but climate change for the moment because climate change needs to be dealt with on its own. It's such a big and emerging issue that to deal with it in just one little section on another lecture is completely unfair. There's a number of ways in which humans have, continue to modify, and will modify stream systems in the future, and we're going to look at those. Some of those, I should say. This list could be almost endless. And as I generally do, here's a guide for what I would like you to be thinking about as you go through this lecture, and then I expect you to return to it. Certainly, we're not going to cover every possible pollutant in the environment that could, or the possible change to the stream ecology based on human impacts, but I want you to see some ways in which human impacts can have very, very strong changes. And then if you were asked about some of these other systems, think about how they might also be modified as a response to that. For instance, I'm not going to deal with trash as you see these people collecting it here, but certainly introduction of trash is a major component of humans' impacts on streams. I thought about doing this, listing all the human impacts and streams in one slide, but it got ridiculous, so I just gave up on it relatively quickly. Instead, what I'm going to recommend you do is take a look at this picture and think about all the different human impacts you can see here on this stream, right? This is a hugely modified system, and yet it's not terribly different from many streams that we see around. And many of the pressures that are on this stream are many of the same pressures that we see elsewhere. And this stream is not, I would say, in a state where it's so degraded that we can hardly recognize it as a stream. It probably still has many of the functions that we associate with streams, but clearly we would recognize that this stream is a highly modified version of the stream that was once present. In this lecture, we're going to spend some time focusing on some really big human impacts, one of those being pollutants, and we'll talk about biomagnification. We're going to talk about eutrophication. Eutrophication we've actually already talked about to a degree when we talked about nitrogen and phosphorus cycles, but we're going to address it again here. We're going to talk about acid rain because that's really important for streams, especially in the Northeast. We need to talk about flow and impoundment from things like dams. All right, so that's a continued and will be an important issue in the future, so we need to spend quite a bit of time on it. And the last one, which I do want to spend at least a little time talking about, is stocking. So the stocking of fishes into streams. Let's start with pollutants. Now, pollutants go by many names. You'll hear them called all sorts of things, right? This sort of boogeymen in the closet. I don't want you to be scared when people say, oh, that's got lots of heavy metals, or there's lots of chemicals in there, or there's toxins. Okay, these terms are very vague. Metals are a group of atomic species. Presumably when you say heavy metals, you mean the heavier ones of those, but it's pretty vague grouping, right? Lithium, one of the lightest elements in the periodic table, is a metal. Does it count as a heavy metal? Chemicals is a term I think that gets thrown around just to scare people. It has no real bearing on anything, right? Everything is chemicals. Your chemicals. So what does it mean when we see chemicals? Toxins, of course, has something about a negative aspect associated with it, but again, it's too vague. So don't be scared by simple names. Make sure you get the specifics when you're trying to understand what a pollutant is. Sometimes we do get a little bit carried away with naming of things or warning people about them. This is a good example, or at least I thought it was a good example of that. This is so vague and so large and so, what's the word, obvious, right? Of course there's chemicals that cause cancer in Disneyland. There's chemicals that cause cancer in your house. There's chemicals in your food that cause cancer, right? That is such a vague and uncertain warning. How would you even act on this besides having to have it posted here? How does that help you at all? Right? I get the idea that, yeah, if you have a storehouse filled with lots of compounds that can cause cancer, you probably want to label that storehouse so that if there's a fire, first responders can know, hey, we shouldn't just go and put the fire out. We should put on PPE before we put the fire out, right? But we need to ask ourselves, what is a pollutant in a stream world? Well, pollutants in streams are broad, all right? So one person's pollutant is another person's treasure, sometimes, except asbestos, right? But nobody wants asbestos. But many, many times when we think of pollutants, they are a byproduct of some process, And the remainder of that material that is not necessary for some process may be useful in another one. So when we say pollutants, we need to be careful that we're being specific. In general, when the term is used, though, it means that it's harmful. All right. And one of the things that's hard to understand about pollutants is if they take years and years to develop problems. So let's imagine you get exposure and then it takes years to develop some sort of response to that. It's going to be very difficult to keep track of that. If a stream is exposed to some chemical once and the effects won't be felt until 10 or 15 years down the road, how are you going to actually know that those two things are linked, right? That's really hard to do. So there are things that we have to be very concerned about, and we should be cautious because if we just add things to a system and we're not sure what they do, then they can cause problems. A common one that we are associated with pollution is lead, and lead is a natural rock, natural metal, but humans have liberated vast quantities of it, okay? We don't use lead nearly as much as we have in the past. Human societies have really used a lot of lead, especially in Europe during the Roman Empire, because it can be melted at very low temperatures and you can physically bend it by hand, and it occurs in really large deposits, so you can find a lot of it in one location. And those features, if you think about it, are very unusual for metals. Very rarely can you work with a metal at low temperatures. Very rarely can you have large quantities of metal and still bend it by hand. And so lead is a really attractive metal for use, especially when you're heating fires with wood, right? You think of, well, it's easy to get really high temperatures if you have a propane fueled fire. Sure, that burns really hot and you get lots of propane. But if you have to go cut down trees, man, does it make sense to use a soft malleable metal that can be melted at low temperatures, because then you have to cut down a lot less trees to use it. In fact, lead was produced in such high quantities in the past that you can actually detect it in ice cores. So here you have a good example of lead levels going way, way up during the Roman Empire, right? You can see that, the Pax Romana there. And you can see that those lead levels go up quite considerably. I'm not worried about necessarily you understanding the scale, other than that you see that that background value goes way, way, way up. Okay? And that's really interesting. That means that the lead in those systems was much, much higher, and that would have entered streams. And the problems that we associate with lead today could have been present and would have been present in certain areas, and probably in large areas in that sort of Roman Empire Europe. Again, very, very interesting. It turns out lead is a neurotoxin, which is really dangerous for all living organisms that have brains. Okay, and yet it is also easily transported by water. So it's definitely in streams. And in addition to that, when humans are moving it, because it's really heavy, it's often transported physically by water. So you have to put a bunch of it in boats and then carry it around. Nobody wants to move that stuff over land. It's so heavy. If you ever get a big piece of lead, you'll understand why. If you make an ox cart filled with lead, you try to get an ox big enough to pull that cart. It's not going to go very far before it needs to rest regularly. So not only will there be atmospheric deposition from humans, and that to a degree still occurs today, you can see that, right? Recent cores are showing lots and lots of lead appearing in them. But in addition to that, you're going to have it be easily liberated into streams, and you're going to potentially do things like cause issues for stream organisms, especially fish. And the problems that humans have with it are going to be very similar to the problems that we see with stream organisms, okay? Humans, of course, have a modified fish body. That modified fish body is going to be impacted in very much the same ways that we see fish in the river impacted. One of the big ones that it causes for humans that's very noticeable is brain damage. And certainly that is a concern in fishes, although probably what you'll tend to see is that fish that have brain damage are going to be easier to catch by predators. They may not behave correctly, they may not breed correctly, and even if they do, you can see that lead actually causes problems with the reproductive system, and we anticipate that would also happen in fish, right? This is also probably going to be happening in things like macroinverts. So these systems are going to be very heavily impacted by things like lead being added to them. Another common pollutant is mercury. And mercury is another metal. Mercury has a number of very serious problems and complications when it enters the body. The three, I should say, major sources of mercury in today's world are fossil fuels, from primarily through coal plants. Metal production, so metallurgy produces mercury, which gets moved into the atmosphere, it gets vaporized. And then actually this other one, which we don't deal with as much, which is artisanal gold mining. And that is actually people using mercury to strip gold out of sediments and soils. And I will also point out that gold mining is often associated with streams and rivers, right? So these things go hand in hand and have for a long time. Mercury, very similar to lead, has a number of very serious health problems. So streams and stream organisms and animals that depend on streams are going to be exposed to this kind of stuff. It deteriorates nervous system. You can do all sorts of things as a result related to hearing, speech, vision, and walking because those require the nervous system, right? It can cause twitching of muscles, damages skin and mucous membranes, and it can cause, again, related to communication from the nervous system to the muscles, difficulty with chewing and swallowing. And mercury, after it enters the atmosphere because of burning, right, eventually gets deposited. It's a metal, it gets rained back out, and it goes into organisms. Now, in the environment, it's incredibly low concentrations, right? So what does this mean that we get enough that it can actually bother us? Well, what happens in streams is that although small organisms don't have very much in them, mercury, it turns out, really doesn't leave the body once it enters. It basically sticks around for the lifespan of the organism. So small organisms pick it up. Those are eaten by larger organisms, right? We're following that size spectra theory. And the large organisms never lose it, so they're always accumulating a little more, a little more, a little more until they get eaten, right? It moves up the food chain and so forth and so on. And the problem is when you eat these large predatory fish, they've had years and years and years of organisms collecting mercury, which they haven't been able to get rid of, and ultimately you're going to eat them. Now, an individual large fish is not going to provide you with enough mercury that's going to be a problem. But think about over the course of your life, right? You're going to eat a lot of these fishes, and all these mercury loads are going to eventually accumulate in your body. And if you can't get rid of them, then you can have all of those health effects, even though no individual fish that you ate ever had those concentrations. And this process of the concentration of mercury accumulating in these organisms across trophic levels is called bioaccumulation. And mercury has and will continue to be very, very dangerous. And you can see that here's a simple fish guide, right? These are stream fishes that you might catch. And many, 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 many states, in fact, I suspect all states put out guides to how you should eat fish. Sometimes you should eat less fish than you would necessarily want because of risks often associated with mercury, right? In addition to that, there's ways in which you can reduce the odds of you getting high mercury concentration. For instance, there may be ways in which you can cut the meat that you can get the lowest contaminated fillets. But you have to be careful about these kind of things, right? And the problem is that there's a lot of different things out there, and there's a lot of ways in which this material can accumulate. Mercury is not the only one. Things like PCBs can also accumulate in the environment. And if you're trying to tell people, okay, these fish in this stream are not safe to eat, or you want to say, well, you can eat some, right, but you shouldn't eat very many. As you start to layer on complexity, it becomes more and more difficult to express that simply until there's confusion about it and people do the wrong thing. Not because they even necessarily want to, but because they simply can't understand it at a deep enough level to do a very complex task, right? You're trying to communicate years worth of scientific study in 2 or 3 sentences or in a picture, and that's very tough to do. In addition to that, if you go to areas where people do not all speak the same language, and this occurs all across urban areas, where there's tons of immigrant communities in urban areas throughout the United States, many of those people maybe they do speak English, but they may not read it, right? Or they may not speak or read English at all, and so you may have to communicate in another language. And if you put up a sign in English, then maybe you also want pictures that are both easily interpreted or easily understood without being able to read it, right? What about kids? There's lots of issues associated with trying to communicate this information. So human impacts with things like pollutants like mercury and lead, while we may be able to limit their effect on us by understanding how they enter into our bodies and then trying to prevent that, we may not be able to limit their effect on the stream environment, and we may have a hard time communicating these very complex patterns to non-specialists, right? Especially when those non-specialists come from communities or cultures that we ourselves do not understand. Let's talk a bit about eutrophication. Eutrophication is this saturation of the environment with what tend to be nutrient limiting resources, such that those resources are no longer limiting, and then you get explosions of primary producers, often in aquatic systems of algae. And these are often unsightly, as you can see here. They're often stinky. They can be dangerous, as we've already talked about with things like cyanobacteria causing releasing neurotoxins. And it is an increasing issue throughout aquatic systems because the number of people around the world continues to grow, and therefore the amount of nutrients that they are releasing continues to grow, and because it's a difficult problem. Streams are always collecting and moving materials from across the landscape, and so it is not helpful if one person exposes large amounts of nutrient and it washes off of a large area, right? It's very easy to imagine, well, just put a cap on that pipe. The vast majority of water entering your system, as you know, doesn't come from a single pipe. It comes from all sorts of areas, right? And it enters a stream by crossing over many, many things. And if one person cheats or one person doesn't do a good job, that can be enough to wipe out many, many people's good work. We're experiencing a similar problem when dealing with, say, COVID-19. Indeed, we have to shelter in place. That is a very helpful way to limit the virus. But if one person does not do that, they can undo many people's good work by infecting many, many, many people, right? And that is very, very challenging because on the one hand, you want to come down on that person and say, okay, we're going to punish you. But to do that takes a lot of resources. You have to find that person, and you also, to some degree, right, start to have to deal with constitutional problems of freedom of choice. They have to be allowed to have some autonomy. And these are difficult issues. And the same kind of issues will come up when we deal with eutrophication and the release of nutrients into water systems. Sure, yeah, we may want to control how much goes out, but also people have to be allowed to use their land. Do you want to reach a level such that you cannot, let's say, make a garden on your own property without asking the local county board for permission and explaining how much fertilizer you're going to use and the size of your garden and how you're going to protect it during the wintertime, what plants you're going to use and how you're going to harvest from it, right? I don't think anyone wants that. But on the other hand, we don't want to see open fields of mud that are saturated with nitrogen and phosphorus that are releasing huge amounts of nutrients into the local rivers and streams. And nutrients come from all over. A classic one that people are often associated with is fertilizers, and absolutely nutrients come from fertilizers, but they also come from animals. They come from the soil and sediments themselves. And so we have to be really careful when we say these are the problem. These people are the problem. Well, the problem is us. It's us generally. There's a lot of sources. In urban areas, you can think of sewage as being an important source of that. You can think of food that you're flushing down your sink. You can think of the ways in which you're changing erosion, such that you're eroding areas that have been able to remain or build up for long periods of time and so haven't been contributing. You can think of the way in which you've deforested regions and converted them from trees which last hundreds or thousands of years, really slow that nutrient cycle down, to grasses and algae, which are lasting years to days, right? That's speeding that system up very fast. If you're in a rural system, you can think about clearing land to grow crops and how you keep cover crops or not, or how you fertilize the soil or how you allow animals near the water. There's a lot of ways in which we modify these systems to increase the rate and the speed that nutrients are moving through them. So we need to be careful when we start to try to point the finger. Humans broadly affect the way that nutrients enter the system, and by and large, we're very, very good at turning the dial way, way up. Okay, and so it takes effort for us to turn it down, and that's humans everywhere. We have to think about how we turn that dial up or dial down. Takes time and money. And I want to be clear that humans have been modifying the landscape for a long, long time. In Maryland especially, one of the early, and I would say the most important crop that managed to make this colony productive was tobacco. And tobacco was well known as a crop, or I should say became well known as a crop that depleted the land of its nutrients very, very rapidly. And if tobacco was depleting the land of its nutrients, then that material was being moved elsewhere, right? Tobacco was largely exported to Europe. Huge, huge market for tobacco. That means all the nutrients that were tied up in those tobacco trees moved into Europe and moved into, at some point, European streams or into European air that eventually rained back down as nutrient in those streams, right? And so we've modified it. We've removed nutrient from one area and moved it to another. And when we abandon fields or when we allow fields to have large muddy areas, right, we provide conduits for nutrient to move into system. Okay, so don't think that this is a problem that has suddenly appeared, but think of this as a problem that is multiplied by very, very large numbers because we're dealing with billions of people now, that has been persistent and an ongoing issue for humans wherever they've settled. What do those nutrients actually do when they get into the system? Well, you already know this, but they massively increase algal production, potentially. They can alter those food webs, right? It is less common that this occurs in streams, although it still does occur. It is more frequent in lakes, but ultimately these streams are dumping into these lakes, so modifications of these streams and modifications of the way these streams operate will have ramifications on humans and on human ecology broadly. Certainly, eutrophication tends to decrease food web complexity in streams, right, by just saturating it with these materials. So we get lots of production potentially, but it's often a very weedy species because specialists are going to be pushed out by species that can produce huge numbers of individuals with a very low quality diet, is what it tends to be. And as we've already mentioned, there's potentially contact hazards, and often we associate all these issues with increased erosion and loss of land. Another issue that humans have dealt with in streams is that of acid rain. So when you burn coal, what you get is nitrogen and sulfur compounds. And just as CO2 combines with water, H2O, to make an acid, so nitrogen, nitrous oxide, and sulfur dioxide can combine with water to make acids, and when those acids rain back out, they will substantially lower the pH of the environment they rain into. In fact, we've actually done a much better job of controlling acid rain. You can see here that it's focused, or originally started around industrial centers where there was a lot of burning of these coal in a very uncapped way, right? So here it is. You can see that really high sulfate concentrations in 1988 and really high nitrogen concentrations in 1988. And by 2008, we had done a much better job. Now we could do an even better job if we wanted to. Technology has improved and we could continue to require or expand the requirement for how coal plants burn. But whether we do that or not is a political decision, and it has maybe not as much to do with streams. In the meantime, acid rain can cause a lot of damage. It causes damage directly to the stream by, say, lowering pH and wiping out a lot of organisms, but it also changes watersheds. It kills trees, it kills plants, it causes, therefore, an exposure and an erosion of soils. It causes issues with how that watershed is. It changes things like how much woody debris is around, right? So these are very, very different systems that get modified as a result of acid rain. So the general impacts, here's a good overview. It also acidifies soils, right? Which is really interesting because it actually also changes the way metals enter waterways. So it actually vastly increases the exposure of aluminum. And it turns out aluminum is actually a harmful pollutant in and of itself, but is normally locked away in soils and sediments. But when acid rain is in contact, it allows that to enter streams. And it can rapidly decrease diversity and effectively wipe out a large number of organisms. This statue over here, I didn't just pick a sad looking statue, was actually eroded, right? You can see that here, was eroded because of acid rain, which washed off calcium carbonate, right? And that, again, a very common element that we find in our stream systems will also have impacts on the ecology of the streams that the acid rain is part of. Another important thing to consider is the way in which we impound and control the flow of water. Now, we've done this for thousands and thousands of years now. Humans, as soon as they've gotten near a stream, have worked on ways to control the flow of that water. But the way in which we do it today is truly massive. So it's probably impossible to find any stream or river that truly has no modification of its flow. And all the large rivers, to some extent, for instance, the United States, have already been dammed. They've been dammed in different locations, but you will find a dam on them. It's impossible not to. In fact, the amount of water that is stored now above ground in lakes behind dams is so large that it actually changes the rotation rate of the Earth around the sun. Now, it's small, I'll give you that, but it's detectable, and that is truly an amazing thing. These impoundments do enormous changes to the stream ecology as well. So they change systems that tended to be flowing to more stagnant. They reduce some of the principles that we have seen, and they expand others that we have seen. So let's look to exactly what I mean by that. Here's an example of a large dam. So large dams do a couple of things here. So this is a river, right, that is impounded. And one of the things that it does is it provides shipping. So you can see that it provides access for shipping. So there's a very deep channel in a place you would not expect it, over by the edge of the stream itself. In addition to that, you can see this enormous amount of aeration that is occurring. In fact, that aeration can get so extreme that it can actually kill organisms, because there can be so much oxygen in the stream that it reaches levels that are beyond anything that organisms usually interact with. It also tends to force flow in certain directions, right? When we think of a stream like this where it's sort of starting to braid, you would expect the water to sort of meander out and be roughly split proportionally between these different branches. But in fact, you could close different branches and have it all go through one section. You're also going to prevent organisms from moving back and forth, right? Organisms are not going to be able to pass those dams easily. And you're going to create very different systems. Where this system was large and deep, there are going to be sections now that are very shallow and that may or may not always flow, right? So an organism that's adapted to a high flow environment is occasionally going to be in a situation where there's no flow, and that's going to create real problems for them, right? Those stoneflies that are really reliant on high oxygen concentrations are all going to die here. So you're going to have a very simplified system. You're also going to modify the total height that the water can go up and down. One of the reasons that dams like this exist are to control flooding. And so you're going to create a very different riparian zone. You can imagine, I think it's fairly easy to do so, that in the past that this island has been flooded. But look, there's power stations on this island. Nobody wants that station to be flooded. And so you must control the height of this river to a very narrow level to maintain an active power station on that island. Okay, so these are real issues that are going to cause major changes. If you imagine you're not going to allow rivers to flood to any serious extent like you did before, think of all the ways in which that's going to change the ecology of the stream further upstream. Think of the way that's going to change the ecology downstream. Man, that arrow came out terribly. This is an example of how you might try to encourage organisms to move by a dam, right? I mentioned that organisms can't move past it. Here's what if you imagine this is the whole area, right? This organism could have moved in the past, and here is what it has to find, this narrow little metal pipe to go through, right? That's a very different system than the one it had before. And it's very modified. This little pipe here is very different from the system that the organism evolved in. And so you're going to have major changes to the way that organisms are utilizing these systems. Also, dams can often flood large areas, and when they do that, they actually produce huge amounts of CO2, okay, because they tend to make lakes, and lakes are CO2 producers, and CO2, as we are going to learn, is really strongly related to climate change. They also create I mentioned before that that thermal structuring of water, well, the top of the water is going to tend to be warm, and when you get into really deep dams, what you'll find is that they tend to draw from the bottom. And so they will tend to export very cold water, but it's going to be really abrupt. You're literally going to be able to stand on one side, and if you're a fish up here swimming around, right, you're going to have water that is pleasantly warm. And then yet, if you get sucked down and out of the dam down here, you're going to have water that is now very, very cold, maybe even as cold as 4 centigrade in the space of just a couple feet, right? Very different systems. You're also going to have a very modified output frequently, which is going to tend to be very small and very fast. So you're going to have very fast flows at the bottom of the dam and relatively slow and slack waters at the top. You're also going to have issues. Dams can also be used for power. And it turns out power turbines, which are really useful for making power, also spin really fast. And organisms that get sucked in go through huge differences in pressure and can just literally die from that. But also, they're turbines, they're big blades, they can just cut them up as well. So for American eels, we think one of the major causes of mortality for large eels is them being killed as they try to move downstream and through dams. I want to be clear, though, that when we think about dams, I don't want you to think, well, all dams are therefore evil and we have to get rid of them. We're not in a luxurious place in sort of human time where we can think about things as good and evil. Things are rarely so clear-cut. Dams can be useful, they can be damaging, but we have to decide if that damage is worth that trade-off, all right? So we can use dams. Maybe dams are really useful at times, but maybe we should be aware that they're also causing damage, right? All of us want the power, and the power from dams is cheap, and it's clean. It doesn't produce nearly as much CO2, especially when it's run-of-the-river types of dams. But it also comes at a cost of the damage to the natural ecology of that stream. Maybe we're willing to take that on some streams and not others, right? So we have to be thoughtful about that stuff. And I don't want you to get into the idea that here's an evil, let's destroy it. But I want you to become more nuanced than that. I want you to be thoughtful about the way in which we deal with environmental problems. We're going to need very thoughtful solutions. And I just wanted to convince you that dams have been around for a long time. Humans have been using water and modifying running water for a very long time. This is an older dam, right? Clearly it's made out of all wood. Humans have been using dam power for a very long time and modifying the systems that they've lived near. All right, lastly, let's talk a bit about stocking. So this is another major impact that occurs in streams. We put fish in streams. And we don't randomly stock species, right? Nobody just goes and says, okay, what's the composition of fish in this stream? We should stock that concentration of fish. People stock sports fish, and sports fish are large predatory fish. And that's because we want to catch large predatory fish. Now, if anything that you've been studying starts to leap to mind, that's good. If you start to stock large amounts of high trophic level organisms, right, you're probably going to have impacts on organisms further down. Okay, so we can anticipate this is going to change the way streams operate, and maybe in unexpected ways. Many, many, many places have a river called the Salmon River. Many of them do not have the native salmon in it anymore, but they have this fish, which is the rainbow trout. Rainbow trout are native to the West Coast. They're native to some rivers, not all, but they've been widely introduced around the world. All right, and so when people often say, oh, I love catching salmon at the Salmon River, frequently they're catching a fish that was never there and isn't the salmon that people 200 years ago, let's say, would have anticipated finding or would have even known about. And that's very interesting because fish that are introduced, or I should say any species that's introduced outside its range, can have profound impacts, often because it's not co-evolved with other species. And so strategies that are successful at avoiding other species may not help you against this novel predator. For instance, if you're a macroinvertebrate and you use a compound to detect a fish in the water, right? These are not smart animals. They don't hang out at the end of the day and discuss what they've seen. They just detect things or don't. If they detect, let's say, some X compound that is produced by a native fish, but this fish doesn't produce very much of that, then they could potentially adopt the wrong behavior because they don't anticipate how many of these predatory fish are around. In addition to that, these fish get released very suddenly, right? One day there aren't very many, And in a matter of an hour or so, a truck pulls up, dumps thousands of these fish into a river, and then these fish have to distribute themselves across the river, right? And so there's a hugely intensive, high pressure predator environment that's pushed in place, right? So these are very, very modified systems. And again, I'm not against stocking fish. Stocking fish is really important for selling fishing licenses. Fishing licenses, it turns out, are really important for providing funding for conservation of many stream bodies. So we have to, again, be thoughtful about what we want to do. Do we want to stock fish? The answer is probably yes. Do we want to stock the same fish everywhere? I don't know. Do you really want to try to raise lots of different fish? That's a nightmare. Also, do you want to really try to inform people about all these different fish and different catch limits and how they're different in these locations? People want to catch the same fish where they go to the same location. So there's all sorts of thorny issues with that, and we have to be thoughtful. As you know as well, of course, people will say, well, they just eat bugs. Well, that's not the case, and also they grow in size, presumably, and at some point they'll be eating your native fish as well. And they rarely eat one thing. And even if they do eat just bugs or macroinvertebrates, as you should call them, there are a lot of reasons why that should make you go, that might cause larger changes to the stream ecology than you would just say, well, it's just a bug, right? Well, there's a lot of ways in which that might change your stream that you have to be thoughtful about. In addition to that, to produce all those fish, we have to have infrastructure. These fish don't just suddenly appear out of thin air. We have to make large systems, and these systems are going to have to draw water from somewhere, often from streams, right? They're also going to have to be feeding these fish, so they're going to make a lot of nutrients that are going to enter into stream bodies frequently. And we're going to have things like land, and we're going to change land cover, right? These ponds are made from probably forested landscape that was timbered that provided access for these ponds. Again, it's not a terrible thing to timber land. We need cleared land to work on. Is it worth it? Is what we have to ask ourselves. And in this particular case, yeah, maybe it is. Maybe we really do want this fish hatchery here, and we say, yeah, it's definitely worth having. But maybe in other places we say, no, it wouldn't be worth it. And maybe more likely there's going to be people on both sides, and the answer may not be obvious, right? And that's where it starts to get difficult. That's where we have to be thoughtful when we think about stream ecology and modifying and using streams for human uses. All right, so next up we're going to talk about climate change. And I made that lecture its own thing because it needs its own coverage. And I'm actually not going to give that lecture. What I'm going to do is post links to a couple of interesting lectures on climate change given by people who are real experts in that field.